Hi everyone, I hope you are doing well. I am Pranav. I welcome you all to SISYAA. Today I have taken a topic from Science and Tech, and by considering the rising importance of science and tech, I have decided to make regular videos on science and tech for civil service examination, and all the videos will be on YouTube channel to give maximum benefits to all the students who are preparing for civil service examination. You all know that before starting any lecture, I just give the blueprint of the video. Let's have a look on the blueprint of the video. In this class, we'll understand about the star, and we'll also discuss about the life cycle of the star. And within the life cycle, we'll discuss the various phases of the life cycle, how the star is ultimately resulted to neutron star, black holes, and what is the relation between black holes and neutron star, what is black dwarf, white dwarf, and what is Chandrasekhar limit, gravitational wave, LIGO observatory, superluminal motion, parallax method, Doppler's effect, blue shift, red shift, etc. We'll discuss everything in detail. You just watch the video from starting to ending and you will get 100% crystal clear concept of what exactly we are doing today. Without wasting time, let's begin the class. So first we'll try to understand the basic function of the star. Yes, first we'll understand the basic function of star. So in order to explain the basic function of the star, I will give you three questions. The number one question, what is the source of heat? What is the source of heat for any star? What is the cause of stability? Cause of stability. What is the, just wait everyone, cause of stability. And in the third point also we'll discuss when did star collapse. Everyone is okay? These are the 3 points I just want to put focus on the first phase of the explanation. We all know that so the star is extremely heated as the star is extremely heated as so the point is where exactly the heat comes from, where exactly the heat comes from, what is the source. So if I say about the source of heat, that is the thermonuclear fusion reaction within the star. What exactly you understand by thermonuclear fusion reaction? Within the star there are so many hydrogen, okay, hydrogen atom that ultimately convert to helium. During the conversion of hydrogen to helium, so a massive amount of energy is radiated from the core. Now this massive amount of energy is resulting the heating to the star. This result what? Heating of star. Heating of star. This ultimately causes the heating of star. Now point is, so this hydrogen is considered as fuel of, this hydrogen is the fuel of star, right? Now the point is this particular energy is radiated outward. Can I say this fusion, thermonuclear fusion, thermonuclear fusion, the direction is outward as, can I say the direction is outward, and there is another force that is a gravity. Can I say the gravity is acting towards the star? This is the inward, gravity is always inward as, and this force is outward, inward, outward, and there is a balance in between gravity and thermonuclear fusion. Now, due to this balancing of gravity and thermonuclear fusion, ultimately the star becomes stable. Yes, we can say that ultimately the star become stable. Why the star becomes stable? Due to the balance between thermonuclear fusion and the gravity. Right? Now, can I say there is a possibility that the hydrogen can be exhaust in the star, or there will be unlimited hydrogen will be available in the star? No. Absence of the hydrogen, that creates absence of the hydrogen, there will be, I can say that absence of hydrogen is absence of hydrogen, there will be no thermonuclear thermonuclear fusion reaction. When there is no thermonuclear reaction, then the only one force that acts upon the star, that is the only gravity acts. When the only gravity that acts on the star, that ultimately what happens, this resulted only gravity that creates a imbalance, and imbalance ultimately resulted to squeezing of the star. The star gets squeezed, and after all, by squeezing more, so there is a explosion, or we can say the star gets collapsed. Now the star, when the star get collapsed, so star get collapsed when there is a absence or exhaust of hydrogen, right? Now there is one more word, that is, so the star is always in the plasma state. What do you understand by plasma? Plasma means what? The group of ions. The group of ions. Basically, the ions are responsible. These are responsible to hold maximum heat. Hold maximum heat, because the star is extremely heated due to the thermonuclear fusion. It is very important to hold that heat. That's what the all the molecules that used to be in the ion form, and that is called what? A plasma state, right? In the next slide we'll understand about when did a star collapse. Already I have explained in the previous. In the core of the star there is a thermonuclear fusion, two hydrogen atom that comes heliums, and the hydrogen atom is considered to be the fuel. And when the star runs out the fuel means there is no hydrogen. That means I can say that there is no hydrogen. In this particular case, the fusion reaction stops. Because of the fusion reaction stops, no energy emits from the core. There is no radiation of energy from the core, and only gravity is acting onto the star. The imbalance between the force of gravity and the fusion force, that ultimately resulted gravity overpowers the fusion force, because there is no fusion. So that resulted in collapse of the star. That is the death of the star. Now the whole process, will try to understand the whole process of the life cycle. Many phases will discuss in detail. Let's have a discuss on different phases within the life cycle. Now first we'll understand the beginning phase of the star. So you have to compare the life cycle of the star to the human life cycle, right? So the way human life cycle, how it happens. So every time birth, death, birth, death. It is a cycle, right? In the same way also, there is a birth of a star and there is a death of a star. Birth of a star and a death of a star. So during the birth, or a very so it's extremely beginning phase of the star, we can say maybe we cannot experience the influence of the star. Maybe the star is not properly visible. So definitely, but the existence is there. It is the extremely beginning phase of the star. that is called a giant gas cloud. This is what I can say, giant gas cloud. After that particular stage, so we can see that there is a protostar and there is a T-Tauri phase. We'll understand the next phase, protostar and a T-Tauri phase. Protostar and a T-Tauri phase, it is also called a formative phase. That means after the birth there is a drastic change. Okay, after the birth there is a drastic change of the formative phase of the star. So these are the protostar and T-Tauri phases, the result of gravitational collapse of nebula. That previously what we have already discussed, that the giant gas cloud, it is a nebula, right? It is a nebula. This ultimately condense, this ultimately contrast and to form, so to form what a protostar and a T-Tauri phase. And also we can say this is to be infant star. Infant star means baby star. This is the baby star. That means not a proper mature star. It's a baby star. It is also not properly visible like a star. It's not too shiny, not proper development of hydrogen fusion. It's a infant star. Now you know that when the star, infant star or a baby star that has a lot of potential, it spins very rapidly like a baby. Baby also runs here and there a lot of time, so spins very rapidly and generate intense heat and temperature. Now that intense heat and temperature was essential, and this heat and temperature keep on accumulating to reach 10 million kelvins. Once the star is reaching to that temperature 10 million Kelvin, ultimately hydrogen fusion that start taking place. Now the hydrogen fusion that start taking place once the star is achieving that particular temperature. Finally the star begins burn. That means we can say this is the beginning phase of the star, or we can say beginning phase means so beginning to become mature, beginning to become mature. This is the phase. Now altogether I can say this is the birth of the star. Once after the birth of the star, we'll get a situation of main sequence. Okay, we'll see about what exactly main sequence. Under the main sequence star, the star live maximum star's life. That means if I say the star's lives 90% of the time, the star stays in the main sequence star. This is the phase where 90% of the star's life that we can see in this particular phase. Now, so what happens exactly in this particular state, in this particular phase, nuclear or hydrogen fusion reaction that already started, because in the previous situation, so the temperature has already reached to 10 million Kelvin. Now we can expect there is a hydrogen fusion, and in the main sequence star there is a hydrogen fusion continuously that happens, that the continuous hydrogen fusion that makes the star to be shiny. You can see that the star is looking shiny, and this is the period. And also we know that the stars are having multiple size. Many stars they are having small in size, some stars are having average size, massive size. Now based on the different size, we can see there is a multiple difference in the consequences. We'll discuss in later. So small, average. So if you get example of sun is an average star. Massive means Sirius is a massive means very big, and very big, and the weight is very, mass is very high. These are called what? A massive. Now example, if I give you example of a fat person and a fit thin person, right? One fat and fit, so I will allow both of them to run in a particular field. What I can observe, so the fat person, as the fat person, here is a fat person. Now the fat person can easily tired, fat person can easily tired. But if I say the same way, so when I say it, a fit person is not easily getting tired, thin person is not easily getting, this is a fit and a thin person not getting easily tired. So in a similar way, when the size of the star is very big, when the size of the star is very big, the mass is very high, it also, the hydrogen fusion also takes at a very rapid rate. Now, due to rapid rate of hydrogen fusion, that ultimately leads the exhaust of hydrogen from the star. And when there is exhaust of hydrogen rapidly from the star, ultimately the star easily get collapse. Big stars easily collapse, small star that remains for a very long period. Do you get that? Now that is what the amount of time a star spent in this phase depends upon the mass. More is the mass, spend less time, burn hydrogen so quickly, a smaller star that slows burn of the hydrogen, right? Now we'll understand. So after this phase, okay, after this main phase or the main sequence star, this is the end phase, okay. After this phase, this is the old age. Do you get that? So this is the birth, this is the mature or the young time, this is the old, and this is the death. Don't you think it's also looking like a human life cycle? Birth, men, young age, old age, and death and remnants. Now, old stage, what happens? The fusion is ultimately restricted. There is no hydrogen fusion. Now we'll understand in the next slide. In sequence, the star gets older. Yes. Now when you can see that when the star gets older, this looks red. This looks red. Now in the bottom side, I have given a order or a collapsing of the star. One example. This example shows for a massive star. And the upper one also, there is an example for a low average mass star. That means if I compare both the size of the star, I can see that the bottom star or the example is a bigger star, massive star, and the upper example is a lower average star. Okay. Now, so now why this color red? If someone will ask you that, so why there is a red color? So you can see that in the given chart, the red color is due to the lowering of temperature. This red color due to lowering of temperature. Lowering of temperature. Now you can see that when the temperature is very high, it looks so clear blue sky daylight. In a daytime, we can see that the sky is completely clear, and of course, so this is what when the temperature comes gradually decrease the temperature, we can see there is a color also changing in that cloudy daylight, cool white LED, moon daylight, evening sun, right? You can see that in the evening sun, the temperature also changes and the declining temperature causes reddish, right? Candle flame. So what we can see in this particular example, when the temperature declines, the color changes to reddish. The color changes to reddish. Or else you can give a easy example to understand. When you melt iron, okay, when you melt iron, you can see that the melting iron looks yellowish and white yellowish it looks. But if you want to get any shape from that particular iron, and then you have to cool down that particular melting iron. After cooling down, so when you try to change the shape of that iron, it looks red. Yes, so that is the reason that when the temperature falls, the color looks what red. Now again the question is why there is a decline of temperature. So this lowering of temperature is caused due to so lowering of, or we can say significant reduction of hydrogen fusion. Hydrogen fusion, there is a significant reduction of hydrogen fusion. That is the reason, okay. Heat, so heat loss, that is the reason there is a heat loss, and heat loss causes the star to reddish color, okay. So heat loss causes the star to reddish color. Understand? Now after that you can see there is a condition supernova. What do you mean by supernova? Now this is the extreme unstable. This condition is defined by extreme unstable. Extreme unstable. And when the star at a phase of extreme unstable, so there is an explosion that takes place. What happens? There is a explosion. Now during that explosion, right, after that explosion, this explosion is called supernova explosion. Now after that explosion, the remnant is resulted as either neutron star or it can be black holes. It cannot be possible there is from one star there is a neutron star and black holes. No, one thing that is possible after the supernova explosion, maybe there is a neutron star, maybe there is a black hole. Okay, now this neutron star or the black hole is possible when the star is very big, massive. This I can say that this is a massive star. Now in the upper side I have given an example of low and average mass. Now in case of low and average mass, so again the same thing, that is a red giant, and after that stage there is a planetary nebula. This is also the stage of explosion. So extremely unstable, extreme unstable, and this is also the stage of explosion. Now what happens in the stage of explosion, you get as white dwarf and black dwarf as a death remnant. So when the star will be low and average, you will get this as a byproduct. When the star will be very massive, you will get an end product is neutron star or black holes. Now the point is, how did you define that whether the star is a big star, massive star, or the star is a low average star? How did you define? The way to define the star is by Chandrasekhar limit. Then the concept came what? Chandrasekhar limit. We'll discuss in detail. So what I have explained, that I have written. So the bottom example is for massive star. Yes, massive star go through the phases. Then after that massive star, in the old days, that super red giant, this is the, then finally it gets extremely unstable and this is supernova, then ultimately resulted into neutron star and or black holes, right? Now in a similar way, low average mass star goes through the red giant, planetary nebula. This planetary nebula and the supernova, these are the stages of extreme unstable and both signifies for explosion. So both signifies for explosion of star. Then after the explosion, the death remnant is resulted into white dwarf, and here you will get a neutron star or you will get a black star. So black holes. We will understand in detail what is the linkage between neutron star and black hole and what exactly you understand by black holes in the next slide. First, again, we have to understand, as I said that, so there is a, how did you define the big or small stars? That is according to Chandrasekhar limit. Let's understand what exactly you mean by Chandrasekhar limit. Now, according to Chandrasekhar limit, any star, okay, so there is a mass of sun. 1.44 times of the mass of the sun is considered as a unit. If any star which mass is less than 1.44 times mass of the sun in this particular case, so this will be regarded as low and average, low or average star. Yes. Now in this low and average star, what is the consequence? White dwarf will be the death remnant. So what will be the death remnant? So white dwarf. So when the star mass is less than 1.44 times of the mass of the sun. If it is more than 1.44 times mass of the sun, so which have mass 1.44 times mass of the sun, will become neither black holes. It will not form a black holes nor a neutron star. It will form what? A white dwarf. A star which is mass is 3 into 1.44 times mass of the sun. Remember, when it will be mass is 1.3 into 1.4 times mass of the sun, you can see that then it is a big star. It's a massive star. massive star. In this case, we will get the black holes. So this is the example of 3 into 1.44, so times 1.44 times mass of sun. Understand, this is the case when the star is having 3 times 1.44 times mass of the sun, then it is called black holes, right? Here in this case, so 1.44 times mass of sun. So this is the case, you will get white dwarf. And in between stages, right, in between this between stage, you will get neutron star. Yes. Now a star which has a mass between 1.44 times of mass of sun to 3.3 into 1.44 mass of the sun, you will get what? Neutron star. This was given by Chandrasekhar, right? Now, point is, in the earlier stage, what I have explained, there is a planetary nebula and there is a supernova. Okay, these are the two extreme unstable phase of the star, where the star collapse happen, the star collapse, or the star explosion happens, collapse happen, everything happens. These are the two stages: planetary nebula and a supernova. During this explosion, what you can say, during the explosion, a lot of jet particles, okay, relativistic jet particles that eject. Of course, when there is an explosion or a collapse that happens to a star, so during the collapse, a many jet particles that started moving from all the direction, right, due to the blast, due to the explosion, the particles or the jet, unusual jet of relativistic particle that spread all around. Yes. Now these particles with a great speed they start traveling. Okay, I can show you in this example. Let me show you that. A unusual jet of matters was observed for the very first time telescope observatory. What is that? So this is what a supernova. Okay, I can say this is what supernova. Now, in this case, supernova, many jet particles, the jet particles is called unusual jet of relativistic particles. Now, they started moving in all the direction, and those particles, they start traveling with a great speed. They start traveling with a great speed. Now, the great speed is measured. What can be the speed of these particles after the supernova explosion? Now we find that these particles, what you call unusual jet of relativistic particle, they travel so almost all 6 to 7 times, 6 to 7 times speed of light. Now it is also a extremely conflict, and it is a contradictory, and it is also practically not possible. We already know no particle can travel more than the speed of the light. Any particle, no particle can travel more than the speed of light. When no particle can move more than the speed of light, then how this unusual jet of relativistic particle can move more than 6 to 7 times of the speed of the light? It was an extreme challenge comment, and it was during the earlier observation. It was the earlier observation that all the unusual jet of relativistic particle, they move in the velocity 6 to 7 times of the speed of the light. Now this was challenged in the current time. It was challenged in the current time. Now it was challenged, and this is challenged by a new concept that is called superluminal motion. Superluminal motion that brought changes, that brought changing of observation and conclusion regarding the speed of unusual jet of relativistic particles. Now, according to superluminal motion, right? So they concluded that the particle velocity is exactly closer lower than the speed of light. When the speed is close to speed of light. So what velocity is close to speed of light, guys? The unusual jet of relativistic particle, this particle after the explosion, when the velocity is close to speed of light, it seems 6 to 7 times faster than speed of light. But this is practically not true. This is not true. Rather, it is a optical illusion. This is the optical illusion he has given, and that name was given. It is an optical illusion. That means whenever this unusual jet of relativistic particle, they start moving with a velocity or a speed which is close to the speed of light, it seems that the speed is 6 to 7 times the speed of light. Rather, it's not a 6 to 7 times speed. It's a just speed is just near to the speed of light. Why you see that the speed is 6 to 7? Because it's not practically true. What we feel that is 6 to 7, but that is not exactly true because of the optical illusion. This optical illusion was proven, and it was given under the superluminal motion. We'll get to that. Observed in the jet of particles released from the black holes. Observed in the jet of particles released from the black holes. So from the black holes, the jet of particles which is released from the black holes, it seems that travels faster than the light. That apparent speed seems to be 6 to 7 times greater than the speed of light. But this actually is an optical illusion. It happens only when the speed of the light when the speed of the particle reaches 0.9 c. C means what? It's the speed of the light. Now, it's not. Now we'll try to understand the parallax method. What exactly the parallax method is about? Okay, please everyone. When I talk about the parallax method, this ultimately, so for making it easy, I am just trying to show a picture. Okay, can you draw two lines in this paper the way I have done? Yes, can you draw two lines? Okay, these are two lines at the reference of background. Okay, these are the background. What I need to do, I just need to fix this paper in the wall. Okay, I just need to fix this paper on the wall. Okay, done. Now what I'll do, I'm just raising my hand. Okay, this hand is the object. Okay, this hand is the object. Do you understand? This hand is the object. Now this is on the wall. Okay, this is on the wall. This paper is fixed on the wall. My hand is the object. Now when I'm raising the hand, what I find that, so I'm trying to look object. This is the object. I'm trying to look this particular object. Do you understand? This object in one eye. Okay, in one eye. One eye means what? So I close my left eye. I close my left eye and I'm seeing that this particular object. Okay, when I'm seeing this object, my hand is object by closing the left eye. So I see that this object is falling, okay, on the first line what we have drawn in the paper. This object is falling on the first line. When I close the second eye, okay, and when I close this the right hand side eye, the object is moving and it is falling on the second line. Now you can see this. You can do the experiment in the room also. Now point is, the objective is in the same position, but when we see different view, when I see from my right eye, it is falling on the right line. So in the first line, when I see from the left eye, okay, when I see from the left eye, it is falling on the right lines. That means with the different view, the object can be seen apparently in the different position. Do you understand? That means my objective is not moving, it is a fixed one. But what I mean, so when I see this object from one eye, I am seeing it in one line. When I see the object in different eye, I can see this object is falling on the second line. This is called what? The apparent shift in the position of object when seen from different position. That means object is not changing its position, rather, so when you see the object, with a different viewpoint, then you can see that, so from different viewpoint, the apparent shift in its position. Do you understand? This is an apparent shift, rather the objective is not shifting, but the apparent movement of the apparent position of the object is shifting due to various viewpoint. Now point is, whenever you are measuring the distance of the star, when you are measuring the distance of the star, so now tell me, so it's very difficult to understand what is the distance. Traditionally, what you used to do? Traditionally, what you used to do? We used to throw a light on the star, okay, and again the light is reflected back. Again, we catch that light, and we just calculate. So incidence and reflection, what is the total time taken, and in that way we just multiply it with the speed of light. In that way, get to know the distance. Do you think that it is a practically in a efficiently we can say that will it be accurate? This answer is definitely not. It is not accurate. Now why it is not accurate? Because when you throw a light on a star, and you are also betting the light can reflect back, you can again catch the light, and you will calculate what is the time taken for the light to reach the star and reflect back to us. This is the way that you will define. Now point is, there are many particles, there are many obstacles, there are many things that comes in between the light, okay. So don't you think the light, the path and the direction is always scattered and differ by any sort of obstacles in the atmosphere, right? This is not exactly the proper way practically to define what is the distance, okay. Now how exactly we'll understand what is the distance between the stars? How, what is the distance of star? Now this parallax method, that how it is used, okay. Now I'm seeing that this is what the position of the object, original position. Can I say this is the original position? Yes, this is the original position of this object. Now you are looking this object from this viewpoint, okay. As I said that when you are changing the viewpoint from this place to this place, okay, so you can see that when you see this from this point, you can see this object is referred at this point. When you see from this point or viewpoint is changing, you are seeing that the objective is looking at this. Now this is shifting from this point to this point, but objective is at this area, okay. Now this is called what? Apparent shift of position. This is called apparent shift of position, right? Now what you need to find is, you just need to find this distance. As you have to find this particular distance. This is the viewpoint and this is the star. Viewpoint and star, you have to find this distance, okay. So in this method, what exactly we know, that if this is the r, this is the theta, okay, this is the theta, right, this is the r, and this length is what? L. Theta is equals to this distance, red arc, divided by L. So arc is what? L divided by r. So I can say that theta equals to L by r. So this divided by radius will get the theta, okay. Now this is an arc. So when the earth is rotating around the sun, can I say this is also a circle, okay, this is also a circle. But the star and the earth, the distance is too much, okay. When the distance will too much, so what will happen? It looks like this. Please try to understand. Just wait, please. Let's say this is the star. It's very far distance. This is a viewpoint, okay. This is the viewpoint from Earth. Can I say this if the distance is very high? When the distance is very high, right? Now let's say this is what the sun, right? Now what we can say that this arc is neglected, and we are considering this arc to straight line. So if I say there is a arc, when the arc is getting smaller by this, when the arc is getting smaller by this, when the arc is getting smaller by this, the arc is getting, so ultimately when the arc will becoming smaller, 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 can I say by making smaller, at the end it looks like a straight line? Now when the distance will be too much, when the distance is short, you can get a big arc. When the distance is, if the objective distance will be far, so we can say there is not a proper curve or arc, rather it looks like a straight line. Now that is the reason we are considering as a base B as a straight line. As this is a B, this is the D, this is the D, and this is what the B. Now B is the base, okay? B is the base, D is the distance, and this is what the theta, right? Now in this way, they start calculating what the distance of star and the earth, or the viewpoint they wanted to calculate, this the distance, okay? Now how exactly? By simple trigonometry, they will, it's not a simple, but it's a very complicated, but in this way, they calculate what the distance. Okay, if I go in detail, then the video will be extremely lengthy. Already the video is becoming more than 30 minutes, so I don't want to again increase the length of the video. So please, so you just, this is what the parallax method. If I get a time, then I will bring some another session to explain. Exactly. So there is a telescope, right? There is a telescope. It basically absorbs the light. Now you understand, when some objective is closing to our earth, okay, when something, a star is close to earth, we can see that when it close, the light will be seen, wavelength will reduce, and the, so higher wavelengths. So okay, now in order to understand the radial velocity, we get the Doppler's effect. What is that? Now this is what the telescope. If a star is moving away, so when the star is moving away, this first example. So when the star is moving away, so whatever light will get from in the telescope, it looks like a red color. Okay. Now it gets stretched out to longer, and the wavelength increases. Yes. Now here in this case, higher wavelength, and because of the higher wavelength, the light seems to be color is what, red. Do you understand? When some objective is closing to the telescope or our viewpoint, then this wavelength decrease, wavelength, the decline, and this declining wavelength causes what, the blue. Now this is called what, the blue shift. This is called blue shift, and this is called red shift. So what is the basic difference between blue shift and red shift? When the objective is close to us, when the star is close to us, that you can find by red shift. When the object is away from us, then we can find it by the, but when his objective is, sorry, when the objective is away from us, we can say that is a red shift. When the objective is close shift, then we can say that is a close to us, then we can say there is a blue shift. Basically, so this ultimately gives one way it is going away, one way it is coming towards us. So one is going away from us, one is coming towards us. This is the way you can understand the radial velocity. One way we can understand what the radial velocity. This is about what, the Doppler's effect. Understand? If a star is approaching towards us, its wavelength increases, decreases, and it is what, the blue shift. So this is the blue shift and red shift. Basically, we understood that when the star is coming towards us or the star is moving away, by understanding the color of the ray. Okay, these are an understanding of a blue shift and red shift, and this is Doppler's effect. Now, within the Doppler's effect, we have studied already. That's all about today's class. Thank you so much, everyone. for your patience and to hold the class till end.